Deep in the ocean, anchored tightly to rocky sediment, sits a dark, leathery capsule continually battered by violent currents. This is a mermaid's purse, the egg case of a skate. While many cartilaginous fishes give birth to live young, skates deposit these capsules directly onto the deep-sea floor, leaving their embryos entirely exposed to a high-pressure, hostile environment. Once deposited, the mother provides no further care. The embryo developing inside is entirely on its own for a gestation period that can stretch from a few months to over 4 years. Surviving that long on the ocean floor presents a severe biological engineering problem. On one hand, the capsule must function as a heavily armored vault, deflecting physical abrasion from sand and resisting the jaws of boring predators. But an impenetrable vault would suffocate the organism inside. As the embryo grows from a tiny zygote into a highly active, gill-respiring skate, its metabolic demand spikes. The capsule must simultaneously act as a highly permeable membrane to sustain constant oxygen exchange. Looking at this collection of 8 documented North Pacific skate species, we can see how they solve this problem. Notice the distinct variations in the curved anterior and posterior horns, as well as the wide lateral keels running down the sides. By decoding the biomimetic laminate architecture and the specific hydrodynamic limits of these varying shapes, researchers are learning exactly how these capsules survive, and that mechanical data is now being used to predict and map undiscovered deep-sea nursery habitats. The physical resilience of the capsule starts at a microscopic level, deep within the walls of the shell itself. If you take a cross-section of the capsule wall, you find an incredibly dense matrix built from 35 distinct layers of collagen protein fibrils. Each sheet of fibers is oriented at right angles to the one directly below it. This orthogonal arrangement functions exactly like modern biomimetic plywood. Because the fibers pull in alternating directions, the shell achieves near-isotropic strength, meaning it can absorb impacts from any angle and stop microscopic cracks from propagating through the wall. But stacking collagen fibers only provides mechanical tensile strength. In the deep sea, a protein-rich capsule sitting stationary for 2 years would be rapidly consumed by bacteria. To prevent microbial degradation, the skate utilizes a biochemical stabilization mechanism known as quinone tanning. Before the egg is even laid, enzymes like catechol oxidase trigger an oxidation reaction within the shell gland, converting catechols into highly reactive molecules called orthoquinones. These quinones chemically cross-link the layered collagen fibers together. This reaction effectively tans the soft membrane, hardening it into a rigid, dark brown shield that resists both external pressure and bacterial enzymes. This tanning process also locks in highly specialized surface microstructures. Looking at these scans, we can see deep water species like Batharaja aleutica develop complex paddle-like projections near their horns, while shallower species like Rajarina are coated in fine, sticky, thread-like fibers. Through this biochemical reaction, a vulnerable biological membrane is transformed into a micro-engineered, multi-year environmental shield. With the embryo safely locked inside a hardened, microbe-resistant shell, a secondary problem arises, drawing fresh oxygen through that armor. The egg case solves this by acting as a natural, passive water pump. As ocean currents move across the convex aerodynamic surface of the capsule, the fluid velocity accelerates over the top. According to Bernoulli's principle, this increase in fluid velocity creates a localized decrease in static pressure, a negative pressure zone called undertryck. This pressure differential literally sucks fresh seawater in through the posterior horns, circulates it over the embryo, and exhausts it out the anterior slits. To maximize this effect, the capsule naturally aligns its long axis parallel to the current, keeping the internal pressure gradient high while minimizing the drag force pulling against the case. This passive system works flawlessly in a steady current. But some skate nurseries are located in slow-moving benthic zones where ocean currents fall below 1 centimeter per second, a flow rate far too weak to drive the Bernoulli pump. To survive in these stagnant environments, the embryo utilizes an active ventilation system. It develops a transitory tail appendage, a specialized biological structure that exists only during gestation and disappears before hatching. The embryo rhythmically beats its tail back and forth inside one of the hollow horns. By altering the available volume in that specific chamber, it creates positive pressure, leveraging Boyle's law. This positive pressure forces stale, deoxygenated water out of the occupied horn. Simultaneously, the pressure shift creates a vacuum effect in the remaining 3 unoccupied horns, forcefully drawing fresh seawater back into the capsule. The skate egg case is an autonomous, biomimetic water pump, capable of operating across drastically different flow regimes. To measure exactly how much current these different capsule designs can withstand, researchers subjected them to physical testing. As seen in this diagram illustrating the experimental setup, they used a motorized tilt table to measure friction, alongside a water flume to measure flow. They were looking for the breakaway velocity, the exact fluid threshold where the force of the ocean current overpowers the capsule's static friction and physical drag, sweeping it off the seafloor. The resulting linear mixed effect models showed that breakaway velocity is determined by a specific interaction between projected surface area, static friction, and the microstructures gripping the sediment. These charts illustrate the flume results for 8 different skate species. Notice the specific data clustering for the big skate, Beringraja binoculata, compared to the deepwater, Bathyrraja trichora. Counterintuitively, Beringraja binoculata has a sleek, highly streamlined shape, yet it recorded some of the lowest abilities to withstand high flow. Without pronounced horns to anchor it, it relies heavily on its sticky, fibrous mats to hold its place in calmer waters. Conversely, the deepwater Bathyrraja trichura capsule features highly rigid horns and complex surface ridges. These microstructures dig into the substrate, allowing the capsule to safely anchor itself in high-flow, deep ocean currents without breaking away. These experiments establish that each species' unique macromorphology dictates a precise, mechanically defined flow regime. Without the exact right current speed, the capsule either suffocates or is swept away into the abyss. When we take these exact flume parameters out of the laboratory and apply them to the global ocean, a clear pattern emerges. This map plots the known geographical distribution of documented skate nursery sites. Notice how the egg cases are heavily clustered along the edges of continental slopes. Specifically, these locations closely overlap with the complex topography of submarine canyons and zones of coastal upwelling. Deep submarine canyons funnel nutrient-rich, freezing water upward. This upwelling generates the exact moderate, well-oxygenated currents required to drive the capsule's passive Bernoulli pump without exceeding the specific breakaway velocity of the species. But the topography making these canyons perfect for skate gestation also makes them prime targets for commercial bottom trawling fleets. Because skates deposit their eggs in massive concentrations, sometimes hundreds of thousands in a single canyon, a single trawl net dragging the seafloor can devastate an entire generation of developing embryos in minutes. To protect these species, ecologists are now utilizing the flume data to build maximum entropy models. By scanning global bathymetry for exact matches in current velocity, depth, and friction thresholds, these predictive models can locate highly probable yet undocumented nursery zones. This allows conservationists to designate protected habitats before fishing fleets arrive. By studying the microscopic biomimetics of a single egg case, we gain the exact data needed to shape macroecological fisheries policy, ensuring these apex predators continue to survive the extremes of the deep sea.